here. This is stop one. We call this the Dalgety Overlook. So we're looking out over this plain here. And the reason we're here is to think about the tectonics of Eastern Australia. And the fun part about this is we have what is colloquially called escarpments here. And these escarpments are very high angle block faults. So when we talked about the building of the mountain range, we were talking about compression. So compression is either really full, folded, deformed sediments that we saw yesterday. I showed you pictures in class of thrust faulting. If we squash them enough, we push rocks up on top. The opposite of that is extension. So this is the result of extensional tectonics. And the concept is that, as we know, we were part of Gondwana when we made this mountain range. We have evidence of subduction, we have evidence of folding and shortening. That was during the compressional stage, so that was something like 300 million years ago. Then we went through a long stage of, we don't really know what happened, but sometime after 300 million years ago, Gondwana started breaking up. Now the details of when a supercontinent breaks up are hard to establish because it does it in bits and pieces, but we know for sure that Antarctica broke away from us 100 million years ago. How would we know that age? Can't all answer at once? Huh? We have a basin between us and Antarctica, and it has a mid-ocean ridge in the middle, and we have concentric basalt. We could get a date for the oldest basalt and know when this happened, right? That'd be a good test question, wouldn't it? So we know that happened. Here on the East Coast, the first sort of evidence we have of things breaking off of here is something like 60, 65 million years ago. And what happens is we took slivers like, crappy old New Zealand, which we didn't want anymore, and pieces of that, and Tasmania, which we definitely didn't want. And all of these pieces of Australia then drifted off eastward, and that was mid-ocean ridge stuff. We just made basalt and moved them out. So we moved all that stuff off, and then at some point we can see here that we have block faulting, and there's a diagram in your handout talking about these two German words, Horst and Graben. Vertical tectonics, block tectonics. You do whatever you're going to do to the crust, you swell it up and crack it, and then a piece drops down. Those pieces are here. These blocks were up here with us. They were part of all of this, and then they dropped down. And so all of Eastern Australia, the Atherton Tablelands, the road down to Wollongong, right, Brown Mountain, here, these escarpments are block faulting of the exiting of pieces of Australia off to the east. Right, we're no longer compressional, we're extensional. So this is what extensional tectonics looks like, is you have steps, and they're very steep because the blocks fall down. But what's interesting is when this block went down, we then have weathering on the high side, and we start to make little alluvial fans of sediment coming off. Alluvium is just a word for clasts. So the material is weathered off the top, gets put into a fan that's taken down by rivers. And we can see that along this escarpment. We can see on the escarpment as you're going to Bungendore, all of Canberra is block faulted. And so as you travel around, realize that Mount Ainslie is sitting up because that's the Horst, and we're mostly in Grabens. So this whole part of Australia has seen that, but mostly we see it out here. Now what happens when we block fault and we rift continents? What does the mantle do? What's my favorite thing? What?
Wine.
Say it again? Other than wine. My second favorite thing. Not arcs, right? Remember? The arc is dead. When we extend it and block fault, we get rifting in the continent, and that allows decompression, melting of the mantle, and we make basalts. So the places on Earth we see basalts typically are hotspots, mid-ocean ridges, continental rifts. So today we're going to look at some of the Monaro Plains volcanics. They are completely different than the arc stuff, and if you see all these little bunny ears out here, that is all basalt. And that basalt is related to this block faulting, decompression of the mantle, melting of the making basalt. Those are not volcanoes per se, but what they are is they are the feeders to volcanoes, and the volcanoes would have been up there somewhere. They've all been eroded off, but when we erode it off, the feeder makes a little thing of basalt which then weathers down and looks like a volcano. So you can see all of those little bunny ears out there. Those are the Monaro volcanics, and their age is 42 million years old, because we can get accurate dates on those. So we know that these escarpments were active at 42 million years ago. So what we want you to do is think about how you make this topography, why it is that we step down to the coast rather than smoothly go to the coast. Every time you want to go to the coast in Australia, you have to wind down a mountain. You have to get down an escarpment. That's because of the block faulting of eastern Australia, because of the extensional tectonics, and because much of what sits out eastward of us was once part of us. And it splintered off and then ventured. So sometimes you rift the continent and it starts a mid-ocean spreading ridge, and sometimes it doesn't. It just has a little bleed up of some basalt and then it stops. That's what happened here. So you want to think about, why did we break this up? It's the same reason that we broke Gondwana up. However, we break up a supercontinent is the same process as how we break this up. And so you want to think about that and talk about it. The basalt is definitely evidence of what happened here. Any suggestions on why we would break off pieces of continents like this? Okay, well, what do we usually call that magma flow underneath?
Plume.
Plume. Right, so one of the models we have for why we break big continents up is we dome them up with a plume. And as that happens, it cracks them because they're brittle. Once it cracks, we could then start to spread it. This is what the East African Rift is doing. It has a plume underneath it, and it's forming what will be a big basin in the future. Some of those then take off, and some of them don't. So somehow or other, we want to break it. And you'll see the cartoon I put in your handout is showing you that if you bend up the crust and crack it, you can then get block faulting, like this. So there's a number of features here out on the Monaro Plain. I ask you to talk about why the Monaro Plain is such a plain, and I'll let you think about that. There's that nice hill over there with trees on it, just a little hill. That's the Berrydale where we're going for lunch. That has the Berrydale batholith sitting underneath it. So it's another one of these big lumps of granite. And what's interesting is that the Berrydale batholith came up and it cooked up the turbidites we looked at yesterday and made them hard and difficult to erode. And so it's standing out there because it's not as easy to erode. Okay, so I want you to sketch then to take a picture and tell me about how we made this sort of topography. So we'll just stay here for a while and we'll wander around and chat, and then if the farmer doesn't chase us away, then we'll go back to the bus and we'll go next stop. So what do you guys think? Comments? Questions? Are you all jiggy with this?
Yes.
All right. So we have some people you might want to chat with here. There's Brad Updike over here, who some of you met. He's one of our